And let me just briefly introduce you, Konrad. So Konrad received his PhD in physics from the University of Oslo in 2008 and had several postdoctoral researcher appointments until landing at the University of Bergen in 2018. And we're really, really delighted to have you here, Konrad. Konrad is truly a world expert in the intersection, the intersection of particle physics and nuclear physics and the application to jet quenching in heavy ions, but also has been branching out into a number of interesting applications of machine learning in that context. So we're just really delighted to have you here to teach us about what you've been thinking about recently. So I will say, are there any objections to recording? We've already started. I don't think there'll be any objections to recording. And Konrad, people can jump in and ask questions as you go.
Of course, yeah, that'll be great.
Wonderful. We're all friends here. So yes, please take it away. Thank you so much.
Yeah. Thanks again, Will, for the very nice, friendly introduction. And again, thanks for the invitation. Yeah, so I have great memories from Cape Town, actually, from hard probes back in 2016, was it, or was it even probably 14,
2013.
maybe.
Yeah, time flies.
Yeah, that was amazing. So anyway, hope to see you guys around somewhere soon. In any case, so today I wanted to give the objective is to kind of give a kind of introductory discussion about the topics that next week I will talk about in more detail. So I think I've kind of recycled some slides that I've been using generally. So please don't get too worried about the very basic introduction. But I thought giving a small introduction to what is QCD and then kind of interesting aspects of QCD in our context, and then what are heavy ion collisions, and finally jets. So the title is Flow and Turbulence, which kind of refers to the hydrodynamic behavior of the quark-gluon plasma, and kind of turbulence is kind of referring to how jets actually get thermal in the medium, how they lose energy, how they dissipate kind of in the medium. So I hope you will enjoy it. So yeah, so the outline of my talk is more or less what I just said there. So let's start with the first part, quantum chromodynamics. So this might be a super basic introduction, but I usually like to kind of place our field in kind of the wider context of particle physics. And of course, it's very funny to actually be able to write down the Lagrangian of the Standard Model on literally a coffee mug. But what people typically see, don't appreciate often is the fact that still the challenge lies in describing dynamical phenomena, right? To describe things that are out of equilibrium, things that are changing, and these quantum processes in that context are still highly up for studying and discovering. But of course, just to set the stage, I mean, what we are trying to use is, of course, the Standard Model of particle physics, and our kind of corners of this huge model is, of course, the kind of description of quarks and gluons in this. Although kind of in heavy ion collisions, recently with increased energy and increased basically statistics from these fantastic experiments at the CERN LHC, we can even measure properties of the Z boson or Higgs boson really in heavy ion collisions. So that kind of sets a bit points forward to this kind of interesting applications of what's called hard probes, where you kind of produce these very rare processes, whether they are heavy particles or very energetic processes in heavy ion collisions. But still, kind of our kind of ballpark is a strong nuclear interaction, and and fundamentally, the strong nuclear interaction is kind of like still very much open. A lot of interesting open fundamental questions. One of them, of course, is just the feature of color confinement, the fact that those degrees of freedom in the standard model Lagrangian are quarks and gluons, but we can never observe them in real life. What we observe are bound states or low energy excitations, low energy bound states of the theory, which then always come in such combinations that you never see kind of the color degree of freedom. So quarks carry a fractional electric charge and a additional color charge, and gluons as well. I mean, gluons are neutral, but they carry a color charge. In fact, this property of color confinement is a fundamental mathematical problem as well. How to generate kind of these kind of massive objects from virtually massless constituents, right? Like the proton mass or the pion. That's really a huge open problem. And I think one problem that is also extremely interesting in a more closer context, of course, some of you guys, is probably also this question about how the spin is generated. So that's something that really will be possible to study in more detail in the upcoming electron ion and electron positron collisions for instance, at BNL coming up in a few years. So kind of this is our ballpark, and it's all kind of boiling down to the fact that gluons can self-interact, right? So the strong nuclear force is kind of similar to electromagnetism, electrodynamics, in the sense that you have a gauge boson coupling with your fermionic fields, which are the quarks. However, the gluon itself, the gauge bosons can have self-interaction. So you have the famous triple gluon and 4 gluon vertices in Qcd. And that, as you probably know very well, is causing the theory to be behaving completely differently from electromagnetism, especially at large distances, right? So, in fact, and this is something that really kind of is kind of probed in collider physics, right? The fact that when you create a quark-antiquark pair, where you maintain them at a specific distance and you separate them more and more, then instead of kind of having this standard picture of field lines that kind of dilute and like you would have for an electromagnetic dipole, at some specific distance scale, the field lines start collapsing into a very narrow string or a very narrow kind of flux tube. Which makes the theory very very different from electrodynamics, which basically would, as you pull charges apart, the Coulomb force will just decrease between them, right? So the field lines will just be rarer and rarer. And if you do the math here, if you take out like a typical value for this, what is estimated for this string tension. And it's funny and this was actually not I didn't come up with this, but a colleague, Alexei Kurkula, came up with actually putting a number on it in terms of newtons, and it turns out that it corresponds to, I mean, the force the force basically becomes constant, and corresponding to that of an elephant in the gravitational field. So basically, it's a constant force of 10 kilonewton, which is basically, telling you a bit why this force is called the strong force, right? So then this is exactly why the whole theory becomes very complicated at large distances, or of the size of a proton, etc. The theory, on the other hand, becomes extremely simple in the opposite limit. When you pull these quarks together, that's exactly where the theory becomes weakly coupled. So this kind of long distance behavior of QCD would be strongly coupled, but the short distance behavior is in principle weakly coupled, and then that makes it amenable for perturbation theory, where basically you can work with it just as you would do for QED, and describe short distance processes in that sense. And then that's exactly why we can use this theory as a tool to study hard energy processes, because large energy processes, by virtue more or less of the Heisenberg uncertainty relation, is something related to the short distance physics. And this property of the theory is exactly what goes under the name as the asymptotic freedom, which basically means that the coupling of the theory grows smaller and smaller with energy, or with kind of energy scale or momentum scale. So, however, kind of solving QCD or kind of studying QCD in more generic conditions is only amenable using brute force kind of numerics, or maybe brute force is not the right word, but basically putting the whole theory on a space-time lattice, or studying it in basically using numerical techniques without much without much theoretical or analytical insight to the theory. So of course we have what I'm trying to say here is that we basically have different regimes of the theory where we can basically apply different tools. But ultimately, the theory is extremely complicated, and still a lot of progress has to be done to kind of merge all the different corners that we understand at the present. So, for instance, lattice QCD is extremely useful for computing QCD in extreme conditions. So you can, for instance, imagine studying nuclear matter, or basically quarks and gluons in a high temperature environment, and that you can do on lattice QCD by simply redefining one of basically the time coordinates. You do so-called weak rotation, and you can study again a discretized theory with a compactified fourth dimension corresponding to basically the inverse of the temperature. And from that, you kind of, from this compactified theory, you can extract properties of the energy momentum tensor, basically. So basically things like the energy density, the pressure, and the entropy. So again, by doing this compactification, you have basically what you have done is that you're studying your theory in the static limit, in the thermal equilibrium limit. But still, there is a lot to be learned from that, and a lot of interesting features. And we see here in this plot kind of the most emblematic feature, which is that you see a crossover behavior between a low energy phase with a low pressure and small energy density and small entropy, and kind of roughly a factor, well, what is it, roughly a factor 5 or 6 increase in all these quantities, right? And this is this crossover temperature is roughly around 155, 160 MeV, which corresponds to 10 to 23 kelvins. And this is understood most easily from just in considering an ideal gas, basically ideal gas of fermions and bosons, and this.
Sorry, please go ahead again.
Okay, great. So you see my screen, right?
Absolutely.
Yeah, perfect. So so I'll just continue on where we stopped. We basically can interpret this this crossover kind of in the thermodynamical quantities as basically the release of new degrees of freedom.
So Konrad?
Yes.
Sorry. Yeah. Yeah. So I'm not seeing it as a full screen. I don't know if you're doing that deliberately.
Let's try again. Do you see the full screen now?
No.
No. So let me. let me stop sharing and try to do it again like this. And now I will share like this. Now you probably see full screen.
Yes, that's perfect. Yeah.
Sorry.
And then, by the way, okay, well, one question. What's on the y-axis on this diagram we have?
On the y-axis, we have the three quantities. So it's the pressure scale by t to the fourth, epsilon by t to the fourth, and entropy by t to the fourth, right? So it's kind of let's say an arbitrary axis where you would plot three curves, three different curves, right? But it's kind of the same order. But what you plot is these quantities, right? With these plotted there. So
the smart thing here is that you've divided out by the units. So the y-axis is unitless.
That's right, exactly. Mm-hmm. So if you would have a completely non-interacting gas of free particles, then you would reach this dotted line up here, and that would be exactly then you could exactly count kind of down here in the lower left. You would have just pions and their degrees of freedom. And up here you would basically have quarks and gluons, which have many more degrees of freedom because they have internal spin, they have spin, and they have color degrees of freedom, etc., etc. So all in all, this gives you this increase. So and this is exactly the kind of the range of temperatures that you would typically probe in a heavy ion collision. So it's not really a kind of non-interacting gas of free particles. There's a deviation from that limit, so that means probably that the quarks and gluons are somehow interacting with each other in a certain way, probably perhaps being quasi-particles or having some thermal masses. But you are far away from being kind of bound states of protons and mesons, right? So it's kind of in the middle here where you would typically place heavy ion collisions. And the second aspect then is that this is again a static system, while heavy ion collisions would explore this in a much more dynamic way, right? You would collide the nuclei, and this quark-gluon plasma would basically evaporate during a few instances. But this plot basically places us somewhere in the middle here in the temperature range of huge temperatures and enormous temperatures compared to the Big Bang, basically. So that's kind of exactly brings us to the next step of the talk, which is discussing heavy ion collisions, and basically the kind of one way to phrase it is to say that in heavy ion collisions we would like to understand some emergent phenomena that arises from interacting from fundamental building blocks of matter that interact with each other, right? So you have quarks and gluons, which are really the not the bound states, but really the fundamental particles of the standard model Lagrangian. They interact, and via their interactions, via their strong or weak interactions, they give rise to emergent phenomena, and we will just come back to them in a second what those are. For instance, jet quenching and flow and things like that. So it's always very fun to kind of give a visual impression of typical heavy ion collision. So it looks like to me kind of like a haystack, right? So what I sometimes say is that instead of looking for a needle in a haystack, which would kind of be, finding a Higgs boson or a supersymmetric particle, we are actually interested in studying the haystack and studying how here you can see the kind of central barrel of the Ellis detector, and all these curves here are tracks of particles that fly out, and what we would be interested in is in learning in the collective behavior and all of this, right? Kind of the generic features of such an event. And this event was created in the collision of two lead nuclei, right? Which collided at almost 1,000 TeV center of mass in total, 1,000 TeV center of mass energy, which is huge. And that means that these, because they're accelerated to almost the speed of light, they're almost, their lores contracted into flat pancakes. And they create basically from the energy that is actually converted in the collision, they create of the order of like 30,000s or tens of thousands of particles, which we exactly can see here the detector. However, as referring back to the kind of the static systems that we just talked about a minute before, but these collisions here, the dense system that is created in these collisions is kind of decaying on much shorter time scale. So it's roughly a few Fermis, which means like 10 to the minus 23 seconds, basically. So so we are talking here about extremely kind of dynamical events and violent events, let's say it like that. So what can we make out of these events? What are the kind of main observables or main kind of features? I also like to show this picture here from the CMS experiment again, where we can see kind of really by event a specific feature, right? So what we see is that that there is a specific, so the blue and red histograms are basically energy depositions in hadronic and electromagnetic calorimeters, and the green stuff are the tracks inside of the detector. Don't ask me for more details because I have no clue. But what we see here by eye is that there is a clear modulation. There's a clear kind of direction in the events, right? There's a clear kind of asymmetry in the events, which simply means that there is kind of a specific direction where there is more energy flowing than in kind of perpendicular to this direction, so to speak. And this is kind of a modulation of about 15%, which is exactly kind of the hallmark, one of the hallmark kind of features of heavy ion collisions. In order to create this kind of asymmetry in the final state, basically asymmetry in the particles that ultimately hit the detector, you would need strong collective effects. So in other words, strong interactions in the sense that those particles would kind of build up a particular specific direction to where they would flow rather than not flow, right? And that can be understood from this simple figure here, which I'm sure you've seen many times. Basically, the fact that in an off-central collision, so not basically head-on, although we'll just come back to what happens in head-on collisions, perhaps. But if you have a off-central collision, you create basically at these energies, most of the kind of blue parts of the nuclei that we see here, which are called spectators, they will just basically continue moving along the beamline, and the stuff that basically got involved in the interaction, they more or less gets just basically stuck in the middle of the detector. Or being expanding along this beam, which is the z-axis here. So what you see here is that initially there is an initial spatial anisotropy, which basically, if we would think about this as a hydrodynamical system, you would say that the pressure gradients along the x-axis here are much smaller than along the y-axis, because the matter is more kind of compressed in the x direction than in the y direction. So these pressure gradients will basically push the particles more in the x direction than in the y direction. In the y direction, they basically flow maybe more or less undisturbed or move undisturbed, while in the x direction, they will be pushed by the pressure gradients of this initial anisotropy. So in order to do that, you need really strong collective effects. You need strong interactions in order to convert that. Of course, if there were no final state interactions, the particles would just randomly, pick a direction and fly in that direction without ever interacting. But because there is pressure, because there is strong interactions, the particles will collide more and more and push each other in a particular direction rather than in another. What happens in a more, this is also kind of a historic development that earlier on when we're thinking about these collisions as basically two pancakes of uniform density. But in fact, what happens is, of course, that you have random positions of nuclei, and they overlap to a certain degree or not. And what you get is kind of typically on the kind of, let's say, Monte Carlo basis of event by event basis, you get a kind of interesting shape of this initial anisotropy, right? It's not necessarily just a pure almond shape, but it could involve some kind of triangular shapes or other higher harmonics. which contribute not only to this azimuthal kind of anisotropy of kind of almond shaped anisotropy, but also to higher order harmonics in the anisotropies.
Check. Sorry. Obviously this is a cartoon, so it's been smoothed out.
Yeah.
But when the two sort of balls pass each other and the chunks get ripped out, is there fragmentation from the spectators? Do they have other bits that sort of fly out and hit the detector, or is it all mostly concentrated in this ball of quark-gluon plasma?
Yeah, they fragment. Yeah, there's a fragmentation region, and in fact that's how you would measure this plane, because the nuclei can collide on top of each other or next to each other, let's say, sitting in the detector itself, and in fact the recoil or this kind of fragmentation dynamics will ultimately hit some detector which sits far away from the collision point, close to the beam. And from that, from the position of energy or particles there, you would kind of make out, what was the plane where this collision happened.
I see.
So there is, you can use different detectors to kind of figure out this plane exactly where it was. Was it, yeah.
All right, thank you.
Yeah, thanks for the question. So again, yeah. So in order to translate these initial anisotropies to final state momentum anisotropies, you really need what's called hydrodynamic flow, and this hints at basically since the system is on its own very quickly decaying, on a time scale, a very short time scale, this simply also implies that it has to kind of reach a kind of conditions for hydrodynamics to apply on also extremely short time scales. And that's what is a huge kind of puzzle, or still debated and still worked on, of rapid hydrodynamization. So it's not really thermalization because it's not completely a globally thermal system with a global temperature. Of course, there are local temperature gradients. But you have hydrodynamization in the sense that you can use hydrodynamics as an efficient tool to describe the evolution of the system. At least this is one of the big paradigms of heavy ion collisions. So having a model for how these macroscopic collisions here actually deposit energy into in the initial moment of overlap, right? Having a model for that, which is again something that you need as an input to hydrodynamics. So you have the initial condition. Hydrodynamics can then allow you to propagate the system forward and see how it evolves. And this is a very nice paper to kind of refer to, because it's kind of so this Nature paper here is kind of giving us a very kind of, I think, nice walk through the main kind of features of what you would like to extract as what you would like to learn from all of this complicated exercise, right? So basically, you have on the left here, I just written down the energy momentum tensor, where the two first terms are kind of typical terms in an ideal gas or ideal liquid. So you have here the two first terms are the famous terms with the energy density and the pressure, and then the blue term here is the shear viscous tensor. So I just wrote it basically kind of in a just illustrative form, in a sense that you have the ideal term and then you have corrections to the ideal picture. And the corrections into the ideal picture would include things like the shear viscosity, bulk viscosity, and higher order transport coefficients. And so you take now your full set of model parameters. So you have some model for the initial state, which is basically drawn out here. This is some model for the initial state, which is called Trento, but it's not really important. Trento has some kind of a parameter that allows you to kind of determine whether the initial state is very smooth, or if it's a little bit more spiky and noisy. So that could hint at kind of nucleonic degrees of freedom being collided, or subnucleonic degrees of freedom playing a role for this initial state. And then it also has as parameters the viscosities, the shear viscosity and bulk viscosity. And what the whole paper is about is to do Bayesian kind of analysis, or basically extracting all of these parameters from the data in a self-consistent way, and explore basically variations of parameters at this and how they compare then to experimental data, how much the experimental data can constrain these parameters consistently. And that's of course a lot of details goes into this about you know, your assumptions and your models and whatever, but in the end it tells us that there is a preferred initial state, and it comes together with kind of which is kind of this one in the middle here, together with the preferred value of eta over s as a function of temperature. So it doesn't really vary much of a temperature, but of course this is kind of part of their modeling. So you see the uncertainties are quite huge. On the other hand, there's also a bulk viscosity extracted at the same time. So we see there is a certain maximum around you know, a lower temperature of the order of 100, I don't know, 180 or something like that. But in the end, this just gives us kind of like nice extraction of all the parameters, and it tells us that basically the eta over s, just taking face value, is extremely small. In fact, the eta over s is 1 order of magnitude smaller than that of a superfluid helium. So eta over s is simply so the quark-gluon plasma somehow has been concluded that it's a very nearly perfect liquid. And that's probably basically mostly because the entropy is so huge. The entropy is huge in these systems, so that makes eta over s really, really small. And then the other interesting takeaway from this paper, this particular paper, so again, with all the caveats, is that the initial state that is being kind of preferred by the data, let's say like that, within the model assumptions, is one where you have a sensitivity to subnuclear fluctuation. So basically some kind of quark-gluon degrees of freedom inside of the colliding nuclei are actually building up the initial energy density and the initial the initial state, basically. So kind of hinting that maybe CGC or some kind of theory like that has kind of a role in describing the initial state of the collision. So from all of this this kind of this particular analysis of this observable, which is this anisotropy in the azimuthal angle, you kind of learn a lot about the quark-gluon plasma. It's a plasma which is almost an ideal fluid with interesting properties like we see here. So that's kind of representative of what's called the soft observables of heavy ion collisions, where by soft I mean where low energy particles are basically multiple. They are dominating completely the observables, and there are most of them, right? They're being created low energy particles, and their collective behavior give rise to very interesting properties like we see here. So these are the soft probes. So now it's basically time to come over to the other side of the spectrum, which is basically the hard probes. There's many interesting hard probes as observables, as well as of course soft probe observables. But here is exactly, again, now we discussed the flow, the hydrodynamical flow of the that we can observe in the probes, and now we're moving over to the jets. And jet quenching is also, again, kind of extremely nicely visualized by again, a screenshot from the CMS detector, or detector, kind of an event display from the CMS detector, where we can see, you know, again, a bunch of tracks. There's a lot of activity, but we can clearly make out on the lower left here something that sticks out, you know, a very collimated energy deposition sitting around you know, about 205 MeV sticking above this background over here, right? So we see that there is a jet being created here. This is a a highly energetic quark or gluon that has been kind of fragmenting and losing its energy and spreading its energy into this cone, right? However, on the other side, and here I'm a bit, I did a bit of a bad job because I actually cut away the main selling point, which is that if you look at the other side, so you would expect energy momentum conservation, right? Leading order QCD processes, you would basically create a back-to-back either quark or gluon or quark antiquark or something like that pair. But you don't see that. You see a significant decorrelation in angle, so they're not completely back-to-back, although that decorrelation is perhaps not that significant. But the most significant thing actually here is that the energy contained in kind of on the opposite side is more than a factor 2 smaller than this energy here. I think if I remember correctly, it's roughly 80 GeV being collected on the other side, this bigger cone here. So this is not really a violation of energy momentum conservation that we observe, but simply the fact that the jet that was created back to back to this high energy jet here probably had to go through part of this plasma that we just discussed in the previous slide. And by going through the plasma, by propagating through it, it lost energy, it was deflected, it was broadened, and ultimately ended up in a bit different direction and with a lot less energy than it initially had. And that's the phenomenon of jet quenching, basically, to put it short. And I probably won't go much into details here, but the idea is basically that, to be quite honest, the picture we have of the QGP from in this regime is a bit different. So that's basically a challenge to myself and to everyone else, I guess. That in fact, I just was telling you that the plasma is almost an ideal fluid, which probably comes from a strong interaction, from a strongly coupled system. But actually, for jet physics, I'm usually the picture I have in mind is a weakly coupled system with a small medium coupling where the plasma consists of quasi-particles. So probably the reality is somewhere in the middle there. But these quasi-particles in this limit of small coupling, the typical momentum exchange between the jet particle, which is the black line here, and the medium particles, which are kind of the red particles, is again the typical scale of the medium. So you could call that the temperature, but in fact it's not exactly the temperature. It's the coupling times the temperature. So this is what's called the screening mass, the Debye mass of the medium. So the typical transverse momentum exchange here is of the order of the Debye mass. And by virtue, again, of the Heisenberg uncertainty principle, the uncertainty in exactly saying when did I scatter on this potential or on this particle, on this massive quasi-particle, is also of the order of 1 over the Debye mass. So, the energy is of the order of the Debye mass, and the time is of the order of 1 over the Debye mass, basically. And it turns out that, so you can think about these scattering centers as massive Yukawa screened basically scattering centers with an elastic cross-section, roughly the integrated elastic cross-section, something like this. So g to the 4th over mv squared. And basically I can work out the mean free path, and it turns out that the mean free path is in this parametric estimate of g being much smaller than 1, it's basically much bigger than the Debye mass inverse. So it basically gives me a picture of a particle, propagating through the plasma. It propagates for a while, then it scatters, then it propagates for a while and forgets everything that happened before, and it scatters again, and then it propagates again and scatters again. So this is kind of a Markovian process where in between the scatterings, you kind of lose all your memory of what happened. That's definitely something that maybe one should think about doing better. But this is the picture we typically have for how jets interact with the medium. And ultimately, the medium itself is of the size L. So if L is much bigger than the mean free path, you basically have to interact many times with the medium. So this is again a picture kind of, here I take the medium as a kind of a static density of scattering centers, a static distribution of scattering centers. But of course, the medium at the same time decays and dilutes. And So this this picture has to also be updated to kind of include other effects like that. And kind of the most emblematic, I mean, if I would devise an experiment, I would do something like more or less like Rutherford experiment or something like that, where you kind of put the quark-gluon plasma in your container and shoot some kind of well-defined or well-calibrated beam through it, right? And this is giving us basically access to what's called the transverse momentum broadening distribution. So what you would do is that you would kind of shoot either quarks or gluons through well-defined container of quark-gluon plasma with a fixed length and a fixed temperature or something like that. And then you would see that on the other side, as these particles go through, you would see a distribution which is not really narrow, but has significantly widened in transverse momentum in the directions perpendicular to the beamline basically. And that's because, again, these elastic interactions, they induce some transverse momentum kicks and they make the particle wiggle in the quark-gluon plasma. And typically, this results would give you a kind of a Gaussian distribution roughly with a width that scales like linearly with L, right? That scales linearly with L. So if you take a smaller box, if you take a bigger box, it will get wider and wider and wider and wider and wider. And how does this Gaussian come from? That's basically through this equation here, which is kind of like a rate equation or kind of like a super simplified Boltzmann equation for exactly this distribution, where you basically say that, well, at some time step t, I have a particle with k minus q momentum, transverse momentum, and then I collide with something in the medium via the elastic scattering potential, which provides me exactly this momentum q. And then, then I end up at momentum k, which is exactly what I want. So this is, and the second term here is kind of a similar thing, a loss term, which you have already a particle at momentum k perp, and then it interacts and gets another momentum and disappears from that let's say that bin, momentum bin. Now, if I do an expansion here, I do a basically Taylor expansion of this first term here. So assuming that Q is much smaller than K, so in other words, assuming that in each collision, I get just a small momentum kick, and overall that builds up to a significant effect. If I do this kind of small angle or small soft approximation here, I can rewrite this equation as a Fokker-Planck equation here. So that's basically because what you get sensitive to, the zeroth order term cancels against, right? The zeroth order in the Taylor cancels with this term. The first order is odd, and you basically pick up on the second term. That's the first term to kind of set in. And the interesting thing here is that, and then exactly we see the meaning of this Q hat parameter, which I haven't mentioned really yet, which is basically the constant, diffusion constant of the Fokker-Planck equation. Although with a small kind of nuance, I included kind of a cutoff dependence on Q hat. So it turns out that this diffusion constant is nothing else. So again, it's the second order Taylor expansion term, right? That sets in, which basically gives me 2 powers of Q. So Q hat is related to the second moment of the elastic cross section. And it turns out that if you assume a typical perturbative or kind of quasi-particle potential here, you'll get this logarithmic sensitivity to the upper cutoff here. So you have to put in an upper cutoff. There's a logarithmic UV divergence, and you have to regulate it somehow. And here we regulated it with the K perp, which is what you would guess because K perp is the other scale here, right? So somehow this diffusion constant it could also have an interesting kind of dependence on the momentum scale, which makes this a bit more interesting, because then you have this Q hat. But again, just neglecting this K-square here will give you a typical diffusion process. So all in all, the process is a bit more involved. You can also have strong hard momentum kicks, and then you'll basically have a hard tail. So basically here is just a is just an illustration of basically what's called the Moliere formula, which basically takes into account these two processes at the same time. The multiple soft scatterings, which gives you this Gaussian shape, and then the hard tail at the large K perp, which gives you basically a sensitivity to the quasi-particles in the medium, which is this 1/K to the fourth is exactly the behavior of the medium potential for quasi-particle scattering. So so one of the interesting directions in heavy physics is somehow to make out the details of this tail, to see if the medium itself, the quark-gluon plasma, has some quasi-particles or not. And people are trying to devise observables to do that. So, however, now to the last part of my talk, which is kind of alluding more now to the next talk, which will be more in this direction, mainly, namely the process of jet fragmentation and energy loss, basically. So, and we will see actually why I included the transverse to broadening is that it's actually very important for how jets radiate in a medium. So we will see that in a second. But already in vacuum, already in proton-proton collisions, already in E+ E- collisions, we have this phenomenon of jets. Basically, if you
sorry,
yes,
can you just go back a little bit more?
Yeah, sure.
Yeah, so a couple slides. So when you showed the broadening being proportional to this this kind of length,
yeah,
right? Is this only assuming these very soft kicks? Does that relationship change when you include the hard kicks?
yeah, it still remains there. Yeah, so hard kicks are rare, right? Hard kicks are rare. So but if because the potential drops with Q, right? It drops with Q to the fourth, 1/Q to the fourth. So the harder Q you want, the more rare process you are looking at. So typically you would exchange momentum of the order of the Debye mass with the medium. Typically, that's the point, right? So the Moliere formula shows us this, that typically you have this the Gaussian in a medium where you have a lot of scattering. Of course, if you have only one, if you have a short medium, right, a small medium, then you only scatter once, and you're sensitive to the effect of only one scattering potential. So then you will be more sensitive to kind of the exact dependence of the scattering potential. But if you are in a large medium and you scatter many times, then you build up this kind of collective effect, or accumulated effect from many soft scatterings. And then it turns out that up to the scale QS, which is Q hat L, you have a Gaussian, and then above that, the Gaussian basically drops to 0, and you start seeing the tail, which is the rare kicks, the hard kicks. Yeah. Yeah.
Oh, okay, thank you.
So the Moliere formula kind of builds in both effects. Yeah. Right. Thanks for the question. So yeah, coming back to the jets now again. Already in vacuum, we have this nice phenomenon of jets, which we just saw in those event displays. In fact, the fact that we didn't really see it because there was a lot of activity in the detector, but we saw that there was a specific direction in the detector where there was a lot of energy deposited. And that's exactly kind of illustrated by this process here. You start out with kind of an energetic quark or gluon that emerges from the hard 2-to-2 cross section. And then in order to become a hadron, it starts radiating gluons and quarks, and in course of radiating, it loses virtuality, and it ultimately becomes pions and protons and whatever at the end, right? And a similar process happens in the medium. So of course, these jets propagate through the medium, and in that case, what we will discuss now are kind of two branching processes. One branching process is the one that always should occur, which is the vacuum one, that also occurs in proton-proton collisions, etc., which we measure in proton-proton collisions and E+ E- collisions. And the other one is a new branching process that is induced by interactions with the medium. And they have very funny properties because they're quite opposite in many aspects. The vacuum shower typically the QCD jets in vacuum typically with higher and higher energies, they would be more and more collimated. All the energy would be more and more directed in a specific direction. That's related to the structure of QCD in vacuum. While the medium processes, again, lead to dissipation, lead to thermalization, lead to kind of spreading out of the energy and momentum over some distance, right? Like this, we just saw about a distance of Q at L or something like that. So what happens in vacuum? So we have this fundamental splitting. Let's just focus on one, and what we get is that well, the famous result is that this probability of such a splitting has two divergences. Basically, whenever the energy of this soft gluon becomes small, you get a divergence formally. And whenever the angle gets small compared to the parent, let's say, again, the spectrum or the probability of splitting explodes. And that simply implies that these are the famous soft and collinear divergences. And that exactly drives a lot of this physics of collimation, of the QCD jets are preferably gluons are want to be emitted along the direction where you already have a large energy flow. So you want to, if you see a hard particle, if you see a direction, and around it, it will always be a lot of activity. That's basically what's going on here. And this typical process, when the time scales of this process is also interesting to analyze, because they go roughly like the formation time of this process, again, related to this uncertainty principle, is roughly like 1 over energy over angle squared. Right, so again, we see here that for a fixed angle, the softer the gluon is, the longer it takes to form, and that's because it's so close, or it's so hard to distinguish it from its original part on that, especially in the collinear limit, right? If you have a very small angle, well, it takes a long time before these two particles kind of separate out, and you actually manage to distinguish them quantum mechanically from one another. So this is really a quantum mechanical effect, which is really which is kind of interesting, right? The funny thing is that in the medium, you kind of modify the whole picture, and you have a lot of interactions, right? And these interactions give you nice dynamics. So, and the nice dynamics is again related to the Gaussian broadening of this gluon here. So now this gluon is being emitted, so it's kind of still a virtual particle, but while it's being emitted, it starts accumulating transverse momentum of the order of Q hat T, right? Of the order of Q hat times some time scale. Now, what is the time scale? Well, the time scale is the formation time, right? So you would simply put in this K-perp into your formation time estimate, and K-perp is depending on formation time, right? So in the end, by solving these two equations here together and putting T formation in here, you get that the formation time is typically of the order of square root of omega over Q hat. So you see, in fact, it's the opposite behavior. So rather the fact that in vacuum, it was that soft gluons take a long time to kind of quantum mechanically decohere or become quantum mechanically distinguishable from their parent partons. In the medium, they are strongly affected by these multiple kicks, by these effects of broadening, and they get quickly decorrelated. They get much more faster decorrelated. So that's basically at the core of the different dynamics of the vacuum shower and kind of the medium shower, as we can call it. And another interesting property is that this the divergence that they have is actually stronger than the one in the vacuums. In the vacuum, we had the omega over omega logarithmic divergence. Here we somehow have a kind of power or fractional power divergence. So it's also very important. So you would tend to imagine that this process would create you a lot of soft gluons that would be very sensitive to again these broadening effects. So I won't go into the details here, but I think I somehow, because I see I'm already run out of time, but basically the vacuum cascade or the vacuum jet fragmentation evolution equations would be called DGLAP evolution, right? And for the medium, well, I don't know, they don't really have a name. It's just called medium cascade or turbulent cascade or something like that. And the interesting thing is that they look very different. In fact, the medium cascade, it basically describes you particles which they have a leading particle that starts emitting soft gluons. They start splitting at shorter and shorter time scales, and in the end, this process is very efficient in transporting energy from the leading particle, which is basically this distribution, and this distribution is the particle that carries almost the total momentum fraction here, right? And it starts distributing this energy into very, very soft modes. And ultimately, these very, very soft modes, they end up at large angles. So I think I will go into more details about this in next week to kind of give you a bit more context there. Just here, I flash this kind of results, which basically tells you that the energy actually goes into zero modes and basically wants to go fast into the thermal bath. And if we also take some other plots from that, you can basically see that, for instance, focusing on the one on the right, that you have, after propagating a certain distance through the medium, you see that so this is the angle on this x axis here, and maybe on the y axis here is the momentum fraction. You see that you have some particles kind of leading on, right? So these are high momentum fractions, almost carrying all the energy, and they're sitting at small angles, right, where there should be. And then they create kind of a tail of soft gluons that are basically more and more spread out in angle behind the jet, trailing the jet, so to speak. So this is exactly the picture we have of how jets lose energy and starts going. Now, a huge open field is kind of how to combine these two descriptions at the same time. And that's probably what I will talk about also next time. How to basically make so right now these plots here assume that there was a single parton flying through the medium. So you don't allow it to radiate in any other way than via medium-induced radiation. But what happens if you have a highly virtual parton that actually initially wants to split into high energy kind of vacuum-like emissions? Well, that's exactly a lot of work is going into that direction, which I hopefully will tell you about next week. So not to drag out, I hope to show you that strong interactions and QCD is an interesting theory with a lot of open questions, and especially the questions related to non-equilibrium phenomena are super interesting, like hydrodynamical flow and also jet quenching goes into that category. That's really still a very active and open area of research. So yeah, to be honest, you see here, mathematics is the language of physics. I also had part of this presentation for a mathematical department, so that's why I have it here, but I still stand behind that statement, right? Anyways, so thanks a lot for your attention.
Super, thank you, Konrad. That was really, really great. I have and people are applauding with the little audio. So I have a number of questions, but maybe let me throw the floor open to other questions that people have at this stage.
Mm-hmm.
I just have a question about the graphs that you're talking about close to the very end, maybe 2 slides back.
Mm-hmm.
Sorry, more slides back.
Yeah.
Yeah, these ones. What is the D sitting over there? Is that?
That's the distribution. Yeah,
okay,
I'm sorry. Yeah, sorry, I was very kind of rushed in the end. But the idea is that you would basically try to simulate this process of multiple splittings. So the initial condition for D is basically just one particle carrying all the momentum fraction, right? So basically a delta function at 1. Yeah. And then you would allow it to split, and after a certain time, T, you would get the distribution.
I see. And then the sort of size difference on the y-axis is telling you just how quickly the spreading is in a vacuum versus a medium propagation.
Somehow, yeah, but actually the most important thing well, the most important thing is that you see here is this amazing scale invariance on the right. So you see below after the peak has kind of decayed, you see that the spectrum here is just completely parallel, right? Which is not the case for the DigiLab cascade.
Yeah.
So the DigiLab cascade, typically, so in other words, typically the DigiLab cascade is one initial particle which emits gluons, and of course they start branching as well. But it's kind of very you still have a very clearly defined leading particle in a DigiLab in a vacuum jet. There's kind of like a core, and there are soft gluons emitted here. Here in the medium cascade, you have much more of a self-similar cascade in the sense that in the low X regime, it's really parallel lines. It's the same kind of steady state spectrum appearing, which indicates that all particles that are being emitted split again on a faster and faster timescale and contribute in kind of preserving the self-similarity, so to speak.
Okay, yeah.
Yeah. So in the DigiLab, basically, there is kind of a preferred momentum scale that moves slowly to the left. That's what we see. While in the medium cascade, there is no particular specific momentum scale where the particles will accumulate. They will just try to go as much down as possible to the left. Ultimately, they will hit the thermal scale, and that's where they will accumulate, actually.
Mm-hmm. Yeah, thank you.
Very good. Other questions? Maybe Gibran. We can't hear you, Gibran. I think you might be muted.
He's having some sound issues.
Yeah.
And do you want to try to just ask the question through my mic?
Hi, it's me, Gibran. Yeah, so again, thank you for your wonderful talk right here. And
Thanks.
a lot of what you discussed was exceedingly relevant to my own thesis. And I just was curious about this medium that you discussed. What other prospective candidates for sort of medias which are in which this regime is relevant?
Yeah, so you mean this picture here, right? Probably. Or so this picture is or maybe you were thinking about this figure.
Yeah, sure.
Yeah. So basically this picture, the weakly coupled limit, is somehow applicable in the right end of this plot. And in fact, it does a good job in describing the right end of this plot if you would assume an equilibrium system of these quasi-gluons and quasi-quarks. So basically, the bi-mass dressed or dressed quark and gluon degrees of freedom. If you would do thermodynamics with these kind of degrees of freedom, which is what's called the hard thermal loop theory, you would somehow get a quite good estimate of this region here. Although when you start decreasing the temperature, you either have to go to exceedingly high loop orders, but you ultimately is going to miss this region here, okay, and this region here, and that's really and it's, you know, you could argue where is the typical energy or temperature range of heavy ion collisions, but most people would probably say that it's really on the lower end of where you could apply or where you have tested HTL, probably. So the medium is probably more complicated than just a gas of screened particles, for sure. But it seems that if you stick to that picture and you just by hand you increase the coupling, you get a quite good phenomenological description. So if you just take a Boltzmann equation and you assume that the particles in the Boltzmann equation are these color screened degrees of freedom, then you actually get a quite interesting dynamics and good qualitative picture. So yeah, I think the jury is still out whether these effects that really sit in this turnover here, how important they are or how qualitatively different they are than just static quasi-particles. But for sure, there is a lot more to be done than this simplified medium model. Yeah.
Thank you.
Yeah, thanks for the good question.
Super.
Yeah, I have a question.
Yes, please
Yeah.
go ahead, Moliere.
Yeah, so yeah, could you go back to the slide, or I guess forward to the slide with I guess you had those two situations of where you were where you were cascading in the medium, and then just keep going a bit.
Yeah.
Okay, so I see these expressions with the how do you what do you have to dial? What knob do you have to dial over here to take you from medium to vacuum?
Right. So
is there a parameter of some sort that I don't see? Or?
Sorry, last sentence, please.
Sorry, I'm just wondering if there's some kind of parameter that you can dial that can take you from the one case to the other.
Oh yeah. Well, Qcd somehow. Right. Yeah. So that's true. I mean, so in the end, what you would do is that you would is Qcd again, right?
Mm-hmm.
Qcd is kind of a measure of the local temperature of the local properties. If Qcd is small, then the typical transverse momentum you could accumulate, right, is going to be super small, and therefore, your intrinsic transverse momentum will be dominating over that. So this is really the approximation where this medium process is kind of superseding whatever vacuum process is already going on, right? So in the end, this K perp squared, here's the sum of kind of the vacuum K perp squared plus the medium K perp squared, and we just assume that the vacuum one is small and the medium is kind of dominating.
Okay.
Yeah. So if Qcd goes down, you would then think that you interact rarely with these medium gluons, or you would exchange very little energy with them or momentum with them, and so in the end it would look like just a vacuum process. Yeah. So the whole magic happens when the medium starts to become dense, and you get kind of bigger effects from the medium than what you would get from the vacuum.
Okay, thanks. I see. Thanks, Konrad.
Thanks.
Well, I like this. Can I follow up just briefly? So in your mind, you're conceptualizing the sort of the dense limit of the medium where you have a very large number of scatterings. Is there a way to capture also the few scatterings limit that's still different from the vacuum?
Yes. Yes, exactly. So that could be kind of, if we would kind of bring the two ideas together between the Moliere formula, right? So we have the Broadening formula, which has this Gaussian peak and then this large momentum tail. If we can bring this tool into the game here, it would kind of be a way to kind of incorporate also hard scatterings. But I guess what you had in mind is also simply dilute media, right? Yeah, in the dilute media, you would basically include only one kick, and then if you remember, I mean, and then there is no Qcd, right? Qcd comes from the fact that you have multiple soft kicks. If you don't have multiple soft kicks, then so you don't have a big enough medium, you will be left with a correction, right? So you'd have a vacuum term plus a medium term where the medium term will somehow be a bit similar to this behavior over here, right? In this right tail. So it will basically kind of In fact, it is very, very similar to this term. It's exactly one of a k-perp to the fourth, which you know very well, right? So it's really the a higher twist term somehow.
Okay, super. I think that's good. So it's, yeah, we always in our field are bumping up against our approximations and trying to make them all self-consistent. And then, yeah, so if one is going into this sort of dense medium picture, then that's the picture that you have. And then if you come in with the dilute limit, it's at least in this case, beyond, you know, so for Moliere, it seems like you're able to capture both sides, but for this transport at the end, you're really baked into the dense limit there.
Yeah, that's right. That's right. So Moliere is not really the correct answer, I read. So because it still assumes a lot of soft scatterings, right? But in a sense, yeah. But in fact, I will talk more about this next week. So I will try to explain also the dilute limit. Yeah.
That'd be very nice. So maybe one quick simple question that I had in terms of this dense limit calculation. So you said that the mean k perp squared that's picked up goes like q hat times, I guess, the formation time. And I was surprised that it wasn't q hat times the length. So could you talk about that a little bit here?
Yeah, so ultimately there will be a length in the game. The length of the medium will come into play because obviously that's the maximal time, the maximal formation time for something happening in the medium, right? It would be length. So that will exactly give you the maximal available transverse momentum, which in turn will give you, and you can immediately see it from the equation down here, that if you put L into the formation time, you'll get kind of the maximal energy, right? Which will be Q hat L squared. So this immediately, again, gives you this limiting energy or momentum scale. So right in the broadening, it was this Q hat times L was where the Gaussian started to drop off and go basically rapidly to zero. And the same thing for this theory, the maximal energy would be omega c, and after omega c, this particular picture would start, being violated. So if you would like to create a gluon with energy above omega c, which is q hat times L squared, you would need exactly to consider dilute limit, right? You would need to assume kick from one hard scatterer. Right. That is the only way you can provide more energy to this gluon. Yeah.
Right. So I think in this picture, you're saying that the gluon is emitted with zero intrinsic k perp, and that all k perp is picked up from kicks from the medium.
Yeah, more or less.
Yeah. So that clarifies that thing in terms of sort of the maximum energy is if you assume that there's no intrinsic k perp. Okay, so then there's a max. But I guess I'm still a little confused. So on this left-hand side, you got the k perp squared goes like q hat t, and so what if your formation time is less than the length of the medium? Are you saying that there's no more k perp that's picked up, or because I would have thought even once the gluon has decohered from the parent, it would continue to gouge and scatter in the picture. Yeah,
you're completely right. So I didn't explain that perhaps in enough detail, but yeah, exactly, you're completely right. So after it has kind of decohered from its parent, it can still broaden. It can broaden and split, however it wants. Yeah. So I didn't really describe this aspect, which is the broadening, right? But you're completely right. In addition to splitting, it could also just broaden out. Yeah.
Okay, super. And that kind of brings me back to just the qualitative picture. You show that really nice CMS plot where you've got this almost back-to-back jet where a wayside jet has lost, it was cut off, but you're saying it's basically lost half of its energy. And how do you conceptualize an object that's lost half of its energy but basically hasn't been deflected? Do you think that this is just an extraordinarily rare event where it's lost a huge amount of energy but stays back to back? Or is this something that's just deeply strange about QCD?
Well, that's a great question. I mean, I think it's part of both what you said, and part of the thing is that this is kind of a rare situation, perhaps. Most of the cases they will be kind of comparable, or the energy loss would be kind of small compared to the absolute value of the momentum, and that's exactly the limit we're trying to work in, right? We in the end, we don't want to completely destroy the jets, because then we would have to go to a completely different framework, like hydrodynamics perhaps, or something like that, right? So we would like to keep the energy losses small compared to the total energy of the jet, so that we have this distinction between a hard and soft particle. But yeah, I think at some point what will happen, right, is also visualized in these distributions, like here, after a certain time, right? So these different lines are for different times, and after a while, you see the peak here at 1 basically vanishes, right? And instead of having a clearly defined guy, a leading particle, you're basically left with kind of a distribution of particles with this funny distribution, right? And that can happen in realistic, well, according to the parametric estimates, it can happen in a collision where, for instance, you're created in the central part of the collision and you have to go out through a long distance in the quark-gluon plasma, right? So some of these emissions are probably, yeah, the jet will just completely disappear, more or less, because you cannot really make out a leading particle, or you cannot really make out a leading, yeah. But why it's not deflected at the same time, that's a good question, yeah. Yeah, that's a good question. So yeah, I think perhaps it's again related to this picture over here, where kind of the high momentum modes are more or less they're acting like kind of just a source of the soft stuff that starts to broaden out, right? And this is basically the full picture would be this picture here, where you have both evolution and angle, and in momentum, in energy. So and you see, so it doesn't really, it's not maybe a completely delta function, but it's much more narrow here than it's here, right? Here it's much wider. So this typical momentum distribution or angular distribution also would depend on the energy of the jet, which I think makes sense also, right? Because if you have a high energy jet, it's mostly, I mean, it can accumulate some transverse momentum, but the deflection angle will be, again, transverse momentum over energy. So if it has large energy, the angle is small.
I guess this is consistent with your dense picture, where you're thinking, I lose just a huge number of very soft guys at no K perp. And so my jet isn't deflected by the emissions. And then all the stuff that's been shed is deflected by medium kicks and rapidly thermalized. Right.
So the leading particle doesn't recoil against it. It recoils a bit, but yeah, it stays more or less on the trajectory. Yeah.
I think Mwande wants to jump in. Please go ahead.
Yeah. I just want to ask, so the CMX picture you showed, that's of a single event?
Yeah. It's a single event. It's kind of a flashy event that they found. Yeah.
Oh, okay. So then, are there others where you do have like a significant deflection?
Sure. There is a distribution of that, right? But most of the but it's true that most of the jets are more or less back to back. And if they're not back to back, that's typically dominated not by medium effects, but actually by vacuum effects. The fact that in Qcd you can emit another gluon and you can get a recoil, right? And then actually those two back to back legs, the next leading order, are not really back to back. So actually, it's in that sense, it's the angular decorrelation is much harder thing to see than the energy. Let's say the energy imbalance. The energy imbalance is much more clear somehow experimentally. Yeah.
Oh, okay. Because I was thinking, like, if this thing is essentially taking a random walk and can be kicked any which way, then isn't it possible that the kicks can average out to like a net very small deflection?
Yeah, exactly. So in that it will give you a kind of just a widening, right? A widening of your distribution. So it's kind of it will become kind of like a convolution of two Gaussians. And so you have to make out the difference between a single Gaussian and two Gaussians, let's say, right? So of similar widths. So that's why it's a bit more difficult to look for the angular deflection. But there might be other observables, or again, I think the main reason is that an angular deflection is basically a transverse momentum over the energy. The typical transverse momentum in the medium is this Q hat L, which is some kind of maybe 5 or 10 GeV maximally, maybe something like that. While your typical jet energy is 100 GeV. So the angle deflection is smaller than one angle. I mean, one radian or whatever. It's 0.1 or something like that. So it's that's why it's a bit hard to make out the angular deflection in this picture.
Yeah, that actually brings me to the last thing I wanted to ask about was so the Moliere scattering in comparison to data. So in particular, some folks say that these jets should be broadened by scattering, but then other folks say there actually should be narrowing. So Matt Sievert and I did a calculation and said LPM effect leads to a narrowing, and Zakharov also in I think a dense limit calculation said that there should be a narrowing. Although to be perfectly frank, I didn't fully understand his paper. So I wonder what you think and where you see the data currently.
Yeah, I mean, I think I also had a look at your paper, Will, with Matt. It's super interesting. So of course, I'm somehow talking about a bit idealized picture, as you say. I mean, it's fair to say that. Where the medium, for instance, in this plot, the medium was assumed to be of a certain fixed temperature, and that's not really probably realistic. So one should definitely look into other corners and study different kind of limits, right, and different approximations. Among them, also the kind of dilute limits. So realistically speaking, it could be that that this picture holds in just a few of extreme events, or so that's, I think, still the jury is out. Another just to when talking about the experimental data, I think it's also important to, at the same time, when we're talking about jet broadening or jet widening, we should also keep in mind energy loss of jets, right? Because if you're what's called kind of a bias effect. So basically, jet quenching, we know from the RAA, I didn't really show the RAA here, but we know basically that jets are shifted quite significantly in jet PT, right? In PT. So you start out with some jet and in some PT, and then actually it's shifted to another PT bin. And what you should then compare to is the jets and what we're comparing to PP data at those the same PT bins, right? So now let's say we had a jet which had the properties of 100 GeV jet, or 200, let's take the CMS picture, right? So we have a 200 GeV jet, and it was shifted down to 80 GeV, right? The question is, did it modify its properties, or did it not modify its properties? That's another question. But I assume it didn't modify all its intrajet properties, its internal properties. You just took the jet and shifted it down and compared it to a 80 GeV vacuum jet. And we just said that in QCD vacuum physics, you get collimation of the jets, right? Energy is more and more located in a smaller angular direction. It's a slow effect. It's a logarithmic effect, but that's the trend. So then you would take a 200 GeV jet, which is narrower than an 80 GeV jet, and you would compare it because they have ultimately the same energy. So that would give you kind of a jet narrowing, right? Wouldn't it? So it's and on top of that, it could be that the jet has some internal modifications, like the ones we are looking at here, right? So whether whether ultimately there is a jet broadening or jet widening, I think also has to take into account this aspect, right? So it's a super interesting question. Yeah.
I mean,
that's nice. I hadn't appreciated this issue of the just the fact that a jet is higher energy, it's narrower. I think we were, in our minds, we were thinking about jet narrowing due to destructive LPM interference, but for you,
Sure.
pointing out that this is a very, very complicated problem.
Yeah, I mean, that would kind of come on top of each other, right? Kind of compete or conspire together.
And there's another side to all of this, right? There are many more complicated jet observables out there than what one would normally consider. Things like these non-jets that are governed by non-global logs, things where you actually force. Well, we select observables, vacuum observables essentially, but you select events that have most of the energy focused into well cones that you prescribe that you can make narrow, and there the emission dynamics becomes enhanced and starts to be very, very similar to what you get at small x with Jimok in the CGC sense. So. Where you start to see, well, in principle at least, this is in the equations, where you start to see things emitted actually notice the other soft stuff that is around. It's just you see the soft stuff that the hard particles shed actually starts talking to each other and starts to, you see nonlinear correlations among those things. Yeah. And I have. You have triggered some interest in me now in actually trying to think of is this similar to medium effects that you actually see, right? I mean, this is sort of a imposed medium by selecting a very, very, very specific subset of events in vacuum physics that wants to feel more collective than others.
Mm-hmm. I think that's a super interesting. If you're thinking about this non-global log, large angle energy flow, that's super interesting. Yeah. Yeah. And it's somehow
because you collimate things by event selection, so to speak, right? you look only at events that look collimated.
Right, exactly. So exactly that's the bias effect. So demanding that I see a jet with jet PT so and so, or an observable and so, that kind of triggers a survival effect, right? I only see the ones that survived into that particular bin, if that's what you mean. So that's kind of the bias effect. Yeah. So I only pick up a subset of specific jets that manage to kind of pass the window.
Yeah, precisely. And that has a specific dynamics one could have a closer look at and compared to medium dynamics in some ways. That might be worth thinking about. Cool.
Okay, guys.
Super. Well, I think this was a really, really good discussion and a great introduction. Thank you very much, Konrad.
Nice. Thanks for the great questions and discussion.
Thanks for the great talk.
Yeah. So